we're going to demonstrate how easy it is to use a MIG welder. The way a MIG welder works is it pushes the wire out of a liner. It's controlled by a simple switch inside the machine. You pull this trigger and it basically feeds out a wire and opens the solenoid that allows the gas to come out. The gas is for shielding and protects the weld. Here's the shielding gas. You'll notice the regulator is set for between 20 and 30 CFMs. That's your high pressure, and this is your low pressure. This is basically a kind of a flow meter. This is not really a flow meter, but this is showing you the flow rate approximately. A proper flow meter has a ball bearing that is very accurate about showing you the flow of gas. Anyway, let's get some welding going on here. Just a quick thing about helmets. If you're getting into welding, get yourself a real good automatic helmet. Do not buy a cheap ass welding helmet. You're only throwing money away. Because pretty much all of them now have a sensitivity dial. That's there for if you're working out in the sunlight or in the dark. You can change it so it triggers at the right times. Maybe you have a welder working right beside you and your helmet keeps switching when you don't want it to. That's what this is for. The shade 10 up to, well, sorry, this machine goes from 7 up to 14. Shade 10 is sort of the average for like burning 1/8 rods or welding 1/4 inch steel. You know, if you're welding some thin sheet metal, you put her down to 7 or 8, something like that. And if you're gouging or something, you might put her up to 13. You're doing some aluminum TIG welding at 300 amps, you might put it up to 14 or more, because that shit is bright. All right, we're going to do a quick pass with this machine, and then we'll start to get into how to make changes with your settings. I have not changed any settings on this machine from when I fiddled with it. I've got a piece of 3/16 angle iron right here. I'm just going to weld into the middle of that, and I've got my machine set at 20.2 and 246. The numbers really don't mean a lot. It's more or less a feel thing. This is your heat, this is your fill. If you're having a problem filling the gap but it's burning good, turn this up. If you're getting a piled up weld, turn this down. If it's too hot and it keeps melting through, turn this back a bit. If when you did that, it starts pushing back the wire, turn this down along with it. The numbers, again, you can put pieces of tape over that. They don't mean shit. It's just sort of a reference. The reality is you change these dials as you need to change them. Do not be afraid to change dials between every single weld. You know, there's people, they think that they can set this up and it should be doing a good job all day long, even though they're changing positions and welding up and overhead and down. And you know, the reality is you are not a good welder if you're not changing these constantly. Making a simple minor change like that just to fine-tune a little weld so you can do a better job, that differentiates you from a quality welder and a hack. So don't be afraid to change your dials. So I'm just going to go with those numbers. This weld may suck, but what it's going to show you is if the weld isn't working out, then we're going to make changes to make it work out. And I'm going to show you how to make those changes. So I'm just going to quickly snip this wire off. Never burn it on the other, you know, some guys will put that gun under the table and burn that off. Don't do that shit. Pros don't do that. So, do a little weld here, see what happens. Okay, it's kind of hard to hold the camera and do this at the same time, but that weld came out more or less perfect. I can't really see too many problems except a little bit of a spatter problem. The weld was a little bit, I think my wire feed was just slightly low. And what happens is you get a little bit of globular action happening there. So the voltage seemed to be pretty good. So I'm just going to make a minor change, not much of one. You see how subtle that was. And we'll try it again. Now you see how that sounded a little bit nicer? Didn't really change the appearance of the weld much, but it eliminated my spatter problem. The balls of spatter were smaller. That'll make them less likely to bond and therefore easier to clean up with a wire wheel or just by knocking them off. They're likely not welded on, but I know you can't see that with the camera, but there's a couple here from the first weld that are, you know, they're almost a millimeter across, and they're definitely welded on. Well, not definitely welded on, but you can probably knock them off. But I'm going to show you something else that, this is sort of your typical short circuit transfer style welding. When you hear the sort of the machine gun sound there, you know, the more you dial that in, the more that sound is smooth. It's not the end all be all of how a weld should go, because I've seen people that, you know, the only way they knew how to dial in the machine was by the sound. Sound ain't important. The end result is important. What this fucking weld looks like is important. And is it fused? Because you can do the most beautiful weld in the world, but if this piece is not stuck to this piece, it don't mean shit. It ain't a weld. A weld is an actual weld. It's not the weld itself, it's the end result is the weld. So I'm going to dial this up, bring this up a notch, and show you what spray arc seems like. The wire's a little small for spray arc, but we're going to blast these volts up to like 27 volts and about 480, 470, and when you're doing spray arc, this tends to be a little bit of a lower ratio than this. They won't be lined up. We're just going to take it from there. Like I said, just set your numbers and don't worry about it. Do a practice run and test it out and see if it is right. If it's not right, make some changes. Okay, that was getting close to being a spray arc weld. It was, as it was warming up at the end there, it was achieving the visual results of a spray arc weld, which is a high degree of wetting and a herringbone pattern. At the beginning of the weld is quite a round profile, and at the end is a V-shaped profile with a line going down the center. To achieve results we're after, we'll see if the volts go up a little more. Maybe we'll put the wire down just slightly and try it again. Try right here. So this is the main benefit of a spray arc weld. It has a beautiful pattern. It's a very flat weld. It wets in perfectly. The downside is occasionally it's so hot it creates undercut at the top of the weld. In this case it didn't, because I didn't quite have it that hot, but you know, if you tune it up too much, you'll get that problem. It's almost impossible to do spray arc in any other position than flat. Overhead I've seen it done, but it's not really practical. Deposit rates are too low. The main benefit is that is almost no cleanup. There's very little, if any, spatter. Super clean looking, super fast, super hot, digs deep. It's a great weld for heavy material, and that if you're going to weld something real heavy, that's the way you want to go. So you see the difference in as the heats went up, right? Like that was much colder, a little hotter, a little hotter, a little hotter. So anyway, I'm going to see if I can just find quickly some slightly thicker material under my bench here. Okay, here's a little piece of shit here. We'll try that. I'm going to just hit it with the wire wheel. Okay, you got any amount of rust on something, you want to get it cleaned off, because when you melt rust, it goes from being a solid iron oxide to a gaseous iron oxide, and all that gasification becomes bubbles inside your weld. If you cut them open, they look like an arrow bar. An arrow bar is not very strong, so you don't want to be holding your ship together with an arrow bar. So anyway, this is a piece of 1/4 inch and this is a piece of 1/2 inch, which makes it a little funny, but we're gonna tune these volts up even more. I don't know how. Oh, that's as far as the machine goes, is 28.5. We'll just leave it at 455, and we'll do a real heavy spray arc. Ideally, it would be almost a silent spray sound, so we'll see how it goes. Okay, that was a real hot weld. You know, I know some people will critique my straightness there, but you try holding the camera and welding with one hand at the same time. It's not really that easy to do, but I think I did okay. So again, I'm not getting my true spray happening, but that's because I'm running the 035 wire. If I was burning 045, it'd do a much better job, but it's not bad for what it is. Anyway, that's the basics of welding a fairly thick material in with MIG welding. Just thought I'd go over what a weld ought to look like, because if you're welding something, let's say you're welding this piece to this piece in thin material. What you need to do is make sure that when you weld this, that it's hot enough to penetrate down into the weld joint. So if it's 1/8 thick, I mean, you don't bevel anything under 1/4 inch really. You just make sure you got a good enough gap. Even 1/4 inch you can do it if you're good, but make sure you got the gap just right to get that one weld down in there, and you know, you won't see much at the bottom, just it'd be just a little bit there, but it's not truly a good weld unless it goes right through. It's really only half of a weld, you know, if it comes up a little bit short under there, in which case ideally you run a pass on the back just to be on the safe side. This is called reinforcement, and this is called your base metal. This is your weld, obviously. When you grind a weld off, you're actually making this whole area weaker than the original. If you leave that weld, as long as it's got a great looking profile, you really should leave the weld. That's why you quite often see welds. You know, people don't clean them up because, you know, if you're an amateur, you think, well, I should grind all that stuff down and make it real pretty. Well, you're doing yourself a disservice, because you're making the overall joint a little too weak. It's, you know, it's close to the original, but it's not 100% as strong, because you have a what's called a heat affected zone all in here, where the metal has been affected by the heat. And you know, that's pretty obvious, I guess. But so this is kind of like insurance, this stuff, this extra bit of metal. So, you know, try to do a really pretty weld, and then you can leave it there and you can be proud of your weld, you know. So a weld profile for a fillet joint, say you ran another piece in here. Now, in small material, it's not a problem to just butt that right up. That there wouldn't be a gap, you know. You just bang it right up against it, and you're going to do a weld here, and you're going to do a weld here. I'm just going to exaggerate what the weld should look like so you can see it a little clearer, but you know, it wouldn't be this big. But the profile, like a cross-section look, should be like this. Okay. It should be slightly humped up in the middle, and this is what they call a wetting in, which means it's a smooth transition into the base metal. What's called undercut is when you've ran this a little too hot and it melted that away and left, you know, if you've done a bit of welding, you know, as an amateur, you'll understand what undercut is. That's where you ran it pretty hot and you didn't have the angle of the gun quite right, or you know, there's a variety of different reasons for getting undercut, but undercut is a serious problem, because you've just taken this, let's just say this was 1/4 inch and you had a decent undercut there. Well, you just turned that 1/4 inch into 3/16. So what was the point of building the whole thing out of 1/4 inch anyway, because it's really only going to be as strong as that weakest point. So you really want to try to control undercut. If you get undercut, the simplest way to fix it is to run another little quick pass in there. You know, it's not going to bother anybody. It's you know, you're kind of doing a little bit too much work there, but it's better than having that weak spot. So don't do it. Set your machine right, and you know, practice. What I'm going to do right now is I'm going to show you a little bit of welding on some 1/8 square tubing, just because that was the first thing I grabbed, a piece of scrap. I turn my machine down to where that would be. Ideally, let's just put her around 19, just as a starting point. What I've got here is 2 pieces of 2" by 1/8 wall square tube. So let's see, if you were actually building something and you're trying to do a nice joint like that, a good square to use, I mean, you can use pretty much any kind of square. Speed squares aren't bad. Any kind of framing square is okay. They tend to be kind of big, so big square, big project. But one thing you want to do is nip the corner off carefully. Don't add a bunch of heat to it, because you may throw your square out a little bit. But this is for small stuff, tubing and stuff. This is sort of the general shop square that lots of people use. Tri-square is what it's called. Works good for lots of tubing and stuff, because you can put it up against the back here. You know, fits in smaller spaces than a speed square or a framing square. And it's used for probably 90% of the squaring work, except for larger things, larger square. So we get back to the 2" square tube that we had. Just gonna make like a T-joint. So I've got that sitting there, and what I'm gonna do is I'm gonna take my tri-square, I'm gonna loosen that up, I'm gonna drop that down to the bottom. And you always want to push that bar, the ruler, back just a tiny bit beyond the surface there, just maybe a 1/16. And with a tri-square, never over tighten it. When you over tighten them, they go out of square. If you don't believe me, check it out. Just crank on them sometime and see what happens to your square. So it should just be just snug enough. Don't cheap out on a tri-square. Make sure it's a basically it's like a cast. I think this is a cast aluminum maybe. Don't buy a plastic one. They're not worth shit. So basically, as soon as you start doing any welding around them, they're just screwed. They'll sit on something hot and melt away. So I'm just going to put this tri-square up against that and check for square. That thing is absolutely perfectly square right now. Likely because this end piece was cut in my, I have one of those dry cutter saws. They're great. They cut really nice with a brand new blade, they do. And very square, especially if you buy a good machine. Some of the cheaper Chinese machines I've used, they're not quite as accurate as mine. Mine's a Porter cable, but you know, you get what you pay for. Twice as much money, it's going to be twice as good, hopefully. So she's dead on square on this side, so I don't have to really worry about anything. When you put a joint together like this, another thing, I don't recommend those triangle magnets, those red magnets, welder's magnets. They're not bad, but they quite often cause a bit of problems. You got to clean them all the time because obviously they're magnetic. They're attracting every single piece of dust and spatter in your shop, and you got to clean them off and make sure there's not the slightest little dingle ball under there or anything like that, because they will mess you up. You're much better off just kind of going by eye, and you know, there are moments where I've used them and they've you know, kind of been the third hand you don't have, and you know, maybe I could design one to hold this damn camera. That might be a good idea, actually. I have to work on that project. So anyway, what you want to do when I'm putting this stuff together, I kind of don't think about it too much. It's sort of on autopilot, but I slap my square against this here, and if it was a little out of square, like you know, it had, say, over a foot, it had maybe a 1/16 out. I guess it doesn't really matter, but if it has any out to it, the side where it's if it's leaning this way, put your tack here on one corner. Never put your tack in the middle. Put one here and go with that one. Don't put it at the outside edge, but put it just on the inside to this side, or the other side, just depends, you know, whichever is more comfortable for you. Then what you do, likely that tack, when you put that tack there, that's gonna pull this back this way through contraction. Quite often it'll pull it right back to where you want it. If it lines up perfectly, then you may want to push it back beyond where you were, that direction, a little bit out of square, but not nearly as much as it was before, and then put your tack on the opposite corner. And then what that does, when that one contracts, it brings it back, and 8 times out of 10, it's pretty damn close to being right on where you want it. Then go around. If it needs to go a little more this way, do that third tack on this side first. If it needs to go that way, then do this one first, right? So, you know, you may not remember that, but that's a good trick for fabricating quickly. You know, you can throw a joint together, a square joint, in a matter of minutes, really. Maybe even a minute, you know, or less. So what I'm going to do, I'm going to just show you without holding it. I'm just going to put a tack there. And we'll see what it does. See if it pulls it back out of square, which it will do. So hold on a second. What you do is put that right in 45 degrees, exactly 45 degrees, start your tack, come down a little bit with it, and then go back up beyond that a little bit, and then back to the middle again, and it'll weld. You'll see some people, when they first start doing it, they just think you hold it right in there and squeeze that trigger and wait. Well, a lot of times it'll hit the bottom a little more than the top, and it just won't be a good tack. So just rock it back and forth like that a couple times. So we got that there. Now we're going to check this for square, and as explained earlier, it will draw. So we do have a little gap there at the bottom because it drew back a 1/16 of an inch over that 9 inches. And so what I want to do, normally I would have held that You know, just with my hand, when I did that tack, if I had held this with a little down pressure, it wouldn't have pulled very much. But in this case, it pulled about a 1/16. So what I got to do now is when I go to the opposite corner, this corner, I'm gonna push down and back this way with my hand, and then put my other tack. So I'm gonna do that now, but I'm gonna have to set the camera down to do that because I don't have free hands. So just hang on a second. See if you can actually see this. Alright, I don't know if you can see that or not, I have to review the tape, but anyway, we've got a good tack there, and we'll grab our square again. She's dead on. She pulled it right back, right where you want it. Both sides are dead on square. Now, what a lot of people don't realize is you don't have to do anything else. This is good enough now. As long as these are good strong tacks, you only need those 2 tacks. Not in every case. If you want to be very, very secure about your project, then go ahead and put 4 tacks, but you know, in some ways you're not being completely efficient. This other tack that's back here now is so strong, it really won't draw this way. So I can run this bead, then I can spin it around and run this bead. Never start your weld on a tack. Start over here and run into that tack. It'll look cleaner and you won't have a big lump where your tack was. That's why I was saying don't put your tacks in here, because when you go to weld and you go over that tack, it's going to be a one shit ass looking weld. So I'm just going to put my helmet on here and we'll weld that out. Okay, here we go. Okay, so there you go. Perfect weld. Has a perfect profile, like with the hump shape in the middle that I was telling you. And we'll check the other side here for square, just to see if it drew a tiny bit. It's absolutely perfect. That weld was run, and you would think that it would draw back a little bit. On this material and this short of a weld, it won't do it if it's held by this one strong tack. That's all it takes. Now, what I was telling you about, if you start this weld on this tack, this is under stress right now because of that other weld. If the heat hits this for a moment, it'll soften it up and then it'll draw that way. So that's why I'm saying never start your weld on a tack. Start it over, you know, away from it. If you had 4 tacks, don't start the weld right on top of the other tack on this side. Just, you know, go in a little bit and keep the strength there. So we'll just weld this other side, get it finished. Exactly the same as the other one. The numbers seem to be pretty good. It was a pretty good guess. Sometimes you get lucky, but those numbers are perfect for this material. So let's just go ahead and weld this out. It's a good habit to get into that when you finish a weld, any kind of gas shielded weld, when you stop, keep the nozzle there just for a split second. Allow that weld to cool. There'll be a little bit of inert gas just kind of falling out of the gun, and that will protect that weld just for a split second. It'll stop contamination of the crater. So we have a decent weld there as well, and now we're going to turn this sideways. We're going to weld our flat. I'll weld it first and then I'll explain some things about it. Well, the irony of that was I just ran out of wire. I knew from a previous video there when I was looking inside the machine that I was about to run out. So anyway, you really don't need to see it to understand it. But what I was going to explain kind of popped into my head. When you're doing any kind of weld, let's say it's a fillet weld, the gun as a starting point should always be, this should be 45 degrees, right? So if this is a 90-degree joint, this should be 45 degrees. When you're doing this flat joint that I was doing before the wire ran out, if you were to look at it sideways, you would have noticed that the gun, I hold the gun so it's straight down. It's completely perpendicular to this weld. It's not like because I'm way over here on the side of the bench that I'm gonna reach out and have the gun running this weld like that. Big no-no. What you're going to end up causing is lots of spatter. You may weld for years and not even understand why you created all that spatter so many times. And if you run that gun straight in there, you will minimize spatter like you wouldn't believe. Same thing as the 45-degree thing there. It minimizes spatter, but on a fillet, it's kind of important to eliminate undercut. If this was a vertical and you're welding a little too much like this, you'll get undercut because the heat's a little too excessive from the arc and it causes this to melt out. It can be caused by many different reasons, but that's one of the most common reasons. Or basically you just got way too much heat. So if you have say you're welding a pipe joint, and there's lots of different angles when you're welding a pipe joint, but it may be like that, and all sorts of weird shapes or what have you. Just need to remember that it's always, you just take this angle right here and just split it in half, and that's where that gun should be. That gun should be, the halfway point. So if it was 60 degrees, then this would be 30. If this was 100 degrees, then this should be 50. Once you get used to doing that all the time, you'll definitely create much nicer weld. A herky-jerky kind of fashion, like welding a little and then moving forward, and welding a little, moving forward. You need to be consistent with your pace across. It should be, you should treat it like, pretend you're a robot for a change, and maintain that travel speed. It can't be up and down. It's got to be very steady, and that will create a beautiful weld, more so than anything. But it's not the only one.